identify a reaction as either acid-base, oxidation reduction, or precipitation. I know last year we learned about the fact there were 5 different types of reactions, which was synthesis, decomposition, etc., etc. Well, when you get deeper into chemistry, all of them fall under 3 categories, and these are these 3 categories. So as far as AP is concerned, they don't care if you know the difference between double replacement, single replacement, etc. They want to know, can you identify it as an acid-base, oxidation reduction, or precipitation reactions? So we're going to be talking about these reactions as one of these 3. Okay. So precipitation reactions frequently involved mixing ions in aqueous solution, in other words, getting them to dissolve, and then producing something that's insoluble, or in other words, it doesn't dissolve in water. Either a solid or a gas, but something that's not dissolving in water. On the AP exam, we need to know that all sodium, potassium, ammonium, and nitrates are soluble in water. Okay. Other than that, pure memorization of solubility rules won't be needed. Okay, but those you'll need to have memorized. Okay. The second learning objective we're going to deal with is knowing that changes in matter can be represented by a balanced chemical equation or a net ionic equation. We can get both of those. We can do it for physical changes. We can do it for chemical reaction. And it tells the identity of the reactants and products and other information about it. Okay? So all physical and chemical processes can be represented symbolically by balanced chemical equations. Chemical reactions can show chemical changes. Chemical changes are always deal with a rearrangement of atoms into new combinations. So, since they're just a rearrangement, both sides of the equation has to have equal number of atoms of every element before and after the change occurred. This demonstrates that mass is conserved, so conservation of mass. Okay. Lastly, balanced molecular, complete ionic, and net ionic equations are 3 different ways that is used to represent a chemical reaction. So the same chemical reaction can be written as a molecular equation, a complete ionic equation, or a net ionic equation. Okay. Which one you use depends upon the context in which it's to be used. And we're going to see a lot of those in the coming weeks. Okay? So, if I'm looking at a reaction for a physical change doesn't have rearrangements of atoms, but it can show something else. For example, physical change of boiling liquid water. I can start with H2O that's in its liquid form represented by the L, and it's going to be changing into H2O in its gas form represented by the G. So a physical change has occurred, but H2O is still H2O. Second example, magnesium chloride can be solid, and I can dissolve it in water, making it aqueous. But MgCl2 is still MgCl2. Okay. Now, if I want to go further and make this what we're going to see in a moment about being an ionic equation, this was a molecular equation. I can write the same thing as an ionic equation by showing what happens when it splits apart. So MgCl2s is a solid. When it dissolves in water, the magnesium ion separates from the Cl ion in that water and it floats around separately. But when the water is dissolved, it's back to MgCl2. So this is a physical change, but Oh, and let me put the 2 in front there because there's 2 of these Cl's. So this is an ionic equation. Both of these tell me the same exact thing. Just one is written in the form that we actually see it in the cup if we were drawing a picture. So chemical reactions or chemical changes can also be represented with an equation. So 2H2, that's gas form, is going to react with O2 in gas form, and it's going to create something new. It's going to create H2O that's a liquid. So now we do have rearrangements of atoms, so it's now a chemical change. And when we have chemical changes, we have to balance the chemical equation to make sure that both sides are equal. Now this one's a pretty complex looking one, so let's kind of look at this and see here. We have 4 different H's, and we have 3 H's. In order to get them the same, I'm going to put a 3 in front of here and a 4 in front of here. That makes 3 times 4 now 12. And the 2 times 2 is 4. 4 times 3 is 12. So H's are now the same on both sides of the equation. Okay. Then I can look at the PO4s. Here there's 4 of them, but here there's another 2 of them. So on this side of the equation, there's a total of 6 PO4s. Over here, there's 2 times 1 for 2 times 3. 2 times 3 is 6. So we have the same number of PO4s on both sides of the equation. Then I can look at the Ca. I have 3 on this side, 3 on this side, and I have a balanced chemical equation. Sorry guys for that beeping. That's my timer going off. I'm cooking food while I'm making this video. So I'll turn that off and get back to the video. Okay, so we have to remember to balance chemical equations as we make them. One type of reaction we studied last year was double replacement reactions. That happened when we had 2 different aqueous substances. AgNO3 was aqueous, and you can see how the Ag and the NO3 are floating around separately in water. They've dissolved. And then we have a second aqueous solution, and you can see the Na and the Cl floating around separately in water because they've dissolved. Double replacement reactions occur when there's 2 things that are aqueous, and when they come together, they form what's called a precipitate. These are going to be classic precipitate reactions. A precipitate is basically when something is not soluble in water anymore, in this case a solid. It could also be a gas that's not dissolved in water. Okay, so in this case we have a reaction that formed a precipitate. Classic precipitate reactions. This is one I can represent in 3 different ways. I can represent this with the molecular equation, which is already written. We can represent it with a total ionic equation. Or a net ionic equation. What a total ionic equation does is it shows what's in this picture. It shows Ag and NO3 going around separately, Na and Cl going around separately, Na and NO3 going around separately, and that Ag formed a solid and it's now together at the bottom. So we simply take this Ag and O3, and there's one Ag, that's a +1 charge, that's aqueous. One NO3 that has a -1 charge, that's aqueous. We have one Na, that's a +1 and aqueous. We have one Cl, That's a -1 charge in aqueous. Whoops. Then we need to draw an arrow because now we're on the other side of the equation. Here we have 1 Na. That's a +1 charge in aqueous. We have an NO3 that has a -1 charge in aqueous. And then we have AgCl, which are together. So we still draw them together. Note, the solid is still written together. Only the aqueuses were written apart. Okay. Now the net ionic equation takes out everything that is the exact same on both sides. For example, Na+1's aqueous, Na+1's aqueous. That didn't really contribute to the reaction. It's called a spectator. Secondly, this NO3 -1 aqueous, NO3 -1 aqueous, it also did not really contribute to the reaction. It's also a spectator. So the real thing that changed here was what was left over. Ag+1 that was aqueous reacted with Cl -1 that was aqueous, and it formed AgCl that's a solid. That is where the chemical change occurred. Okay. Now down here it gives the definition. Total ionic equations. It says, since soluble ionic compounds are actually dissociated into their ions, we can more accurately represent this with a total ionic equation to show each ion individually. Because in reality, in that cup of water, they really are floating around as individuals. Okay. Notice that all the insoluble products remain together. So the AgCl that was not aqueous remained together. It remained together here, here, and of course in the molecular equation. Okay. All right. Now, since some of the ions are not actually a part of the change, we can drop those out. These are called spectator ions because they do not participate in the reaction. This equation here is what I just showed right there. I dropped out the Na as a spectator and the NO3 as a spectator because it didn't change. It wasn't really a part of what changed in that reaction. Okay, so we just drop them out of this net ionic equation. So the net ionic equation is useful to seeing what really happened in the reaction outside of just everything that's floating around in the cup. All right, so when I look at this, another example of a double replacement reaction that's actually a precipitate reaction. This is aqueous and they're floating around separately in water. This is aqueous and they're floating around separately in water. And when I finish, these two are still floating around separately in water. And one of them is together as a solid at the bottom, represented by the equation, the molecular equation. This is typically what we drew most of the time last year as the equation. And this is a correct version of an equation. It's very useful when you're wanting to see everything that you need to put in that cup to make this happen. But if I'm wanting to see what really is happening on the molecular level, I'm going to want to do a total ionic and a net ionic equation. So here we have one Cu. That Cu must have a +2 charge because Cl is -1 and there's two of them. And if they add to 0, the Cu must have a +2 charge. Then we have our Cl, which is a -1 charge, aqueous. And there's two of them. So I'm going to draw the two in front to show there's two of them floating around separately. Because in reality, that Cl and that Cl are separate in the cup. That's why I draw the two in front. Then I have Ba, which is a +2 charge. Then I have my OH, aqueous. Then I have my OH, which is -1 charge. And over on this side, this is solid. So I do not separate it. It stays together. Because in the bottom of the cup, it will be together. If you did the double replacement reaction last year, you remember that a solid formed at the bottom of the reaction when we did this. A solid actually came out and got to the bottom, and it was together. Okay. Plus Ba, which has a +2 charge, and it's aqueous. Plus, there's 2 of these Cl's, so 2 Cl's that are -1 that are aqueous. Okay. This is called the total ionic equation because it shows the ions separately, and it showed every single thing, spectators and what really participate in the reaction. Now, what I want to do is I want to go and remove the spectators. So Ba +2 aqueous, Ba +2 aqueous, that is a spectator because it's the same on both sides. We also have 2Cl -1 aqueous, 2Cl -1 aqueous. That's also a spectator. And I can say that Ba +2 and Cl -1 are my spectators. And that would be an acceptable way of writing it as well, of this answer. Now, when I go to the net ionic equation, I'm going to write everything that's not a spectator. So what was not a spectator was Cu +2 aqueous. That ended up reacting with this OH -1 aqueous. And it formed CuOH2 that was not aqueous, it was a solid. So a change happened. So these are what I wrote down as my net ionic equation. Now, if I want to know what was really happening in that cup that formed a reaction, it was really this. It was the Cu and the OH that was reacting together, nothing else. Okay. All right. Now, something that you can memorize, it'll help you out, something you'll need to memorize, is that the following are always spectators. Na+, K+, NO3 negative, and H4 negative. So when I look at these following examples, NO3, anywhere it is, I know it's a spectator. Okay. NH4, I don't see any NH4 in those equations. K+, I don't see any K+. Na+, I see Na here, and that's all. So right there, I know they're spectators even before I draw an equation for this. Now I can quickly check and see if I want to do the net ionic equation and skip right in the total. I can kind of look right now and see, is the rest of it make a change? Do I have Ag aqueous on the other side? And the answer is no, I have Ag solid. Do I have SO4 aqueous on the other side? The answer is no, I have SO4 solid. So now I can skip straight to my net ionic equation if I know this. If I can recognize the spectators right away, I can jump straight to the net, which is 2 Ag, which had a +1 charge, that was aqueous, coming from there. This 1 SO4, well, I don't have to write the 1 in front. Okay, SO4, that's a -2 charge, it's aqueous, and it forms this Ag2SO4, that's a solid. On this next one, we can double check this as well. Is Sc solid on the other side? No, it's aqueous. Is Ag aqueous on the other side? No, it's solid. Okay, so this must be part of the reaction, not a spectator. So, Cs, solid, reacts with 3 of these Ags, which has a +1 charge, and they're aqueous, to produce 3 Ags that are solid and this SC that is aqueous. Now here I need to do a little bit more. Aqueuses need to show their charge. This one, I don't know the charge on SC, but I do know the charge on NO3. That's -1, and there's 3 of them. I know everything adds to be 0, so SC must be a +3 charge. And I've got my net ionic equation. Now the last one, there was no obvious obvious spectators in here. So I can do the total ionic equation and then the net, which is what I will do. But I can also, if you're able to see it, I can scan this and see, is there any changes? Is there any spectators? Ca solid, Ca aqueous. That can't be a spectator. Okay, let's see. CO3 solid, I don't even see CO3, but I see CO2 gas. That's definitely not a spectator. H that's aqueous, H that's liquid. That ain't a spectator. Cl that's aqueous, Cl that's aqueous. That's probably a spectator. In fact, it is a spectator. It's not one of my known ones, but I can kind of do this visually. But for those who can't see it very well, I'm going to write out my total, then my net. Okay. So my total ionic equation would look like this. This is solid, so it stays together. This is aqueous, so I'm going to break it apart to the 2 H+1s that are aqueous and 2 Cl -1s that are aqueous. This is aqueous, I'm going to break it apart. Ca +2 that's aqueous and 2 Cl -1s that are aqueous. This is not aqueous, I will not break it apart. CO2 gas. This is not aqueous, I'm not breaking it apart. H2O liquid. If you scan both sides real quick, you'll realize the only thing that's the same on both sides is that one I kind of identified earlier. That's my spectator. The rest is my net ionic equation. So the CaCO3S plus the 2H+1 aqueous, which yields Ca +2 aqueous, plus the CO2 gas, plus the H2O liquid. That's my net ionic equation. Everything but the spectator. And the spectator, the one who didn't really participate in the reaction but was just there, is my Cl -1. Okay. So one thing to kind of keep in mind, because if you don't see this, the reason I'm introducing this early, even though we're going to be using it a lot later, is because most of the time, people have difficulties with this because the AP test and these other stuff, they'll show you the net ionic equation and they won't explicitly say this is a net ionic equation. And it can be confusing because you're like, wait a minute. If I read this problem, which says a student studying the reaction represented above constructs a voltaic cell as shown in the diagram below. The cell contains a Au solid electrode in a beaker containing 1 molar of AuNO3 aqueous and a platinum solid in a beaker containing 1 molar CuNO3 and 1 molar CuNO3 too. Okay? And you're looking at that and you're going, here's the net ionic equation, but if you don't realize it's in that, you're going, I don't see Cu plus in this problem. I see CuNO3 or CuNO. 3, one has 2 behind, one doesn't. I see Au +3 aqueous. I don't see that anywhere. I just see that. And it can be confusing. So the biggest thing to remember when you're dealing with net ionic equations, or you might be, is you need to remember that when given a net ionic equation, they're actually spectator ions that are not seen in the equation. There's things floating around here. Okay? Now, you will never have to construct a molecular equation from the net that I know of. If I'm wrong and I find out later, I will change that. I've never seen that from what I remember, so right now I'm going to say that, and if we realize later on in the year that's different, we'll show you how to do it and make you responsible for it. But I'm just going to do it right now just because. We know there's some Cu plus that's aqueous in here. Okay, so I see Cu here and I see Cu here. I know NO3 is a -1 charge, and there's only one of them, so this must be a +1 charge. Over here, I see NO3 is a -1 charge, but there's two of them. This must be a +2 charge. This one here is written +1, so that must be this here that we're looking at. Cu, if I write it correctly here, CuNO3, that's aqueous. And here I see an Au +3. Well, we know, I don't see this connected with anything, so it doesn't really have a charge. But this one I see NO3, which is -1, and there's 3 of them. This must be a +3 charge. So this must be the one that's represented here. And these were aqueous. Okay. Now this here, we see the Cu +2. We just saw a few moments ago that this one is the one that had the +2 charge. And then lastly, we have Au solid. Well, here's Au solid. That's the only one that matches in the problem. So this is the real molecular equation. And if we were to balance it, we would see the numbers too. I'm going to cheat, because they already told me the number in front of this one. And they already told me the number in front of this one. And I can just double check and make sure they're balanced correctly, and they are. Okay. So my point on this one is that when you saw, now what I kind of gave you more than you needed, but I wanted you to see the full picture. Okay. The biggest point is that when you see this as a net ionic equation and they do not give you the molecular, know that somewhere this exists, where you can actually see what's going on in the substances here, 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 and here, even though this doesn't look like it. Know there's a molecular equation there, and that the rest of these things that are not in this net is because they're spectators. NO3 is always a spectator. That's why it wasn't written in the net. Okay. All right. So y'all can practice the problems, and I will get the next video up and running.